Okay, so you've had some time to give some consideration to which of these are rational, and based on the definition I've given you there, it says a rational function really is a quotient of two polynomial functions. So it's a matter of just taking a look. Let's take a look. That's definitely a polynomial function. That's a polynomial function. This is the quotient of two polynomial functions, so it would be rational. Taking a look at that, that's not polynomial. That part isn't polynomial. So this couldn't be a rational function because neither the numerator or denominator are polynomial functions. This is definitely a polynomial, and this is a constant. So we would not classify this as a rational function because the denominator is a constant. We could really just divide each of these and say this is 2x to the fourth. I'm going to finish that over here. Minus 7/4 x, and then plus 1/4. And you can see that that definitely is a polynomial. Now let's take a look at this one up here. This is not polynomial. Right here, non-polynomial. So therefore this cannot be a rational function. Rational functions, if we're going to look at domain and range, kind of extending the ideas from yesterday. So the domain and range of all real number will be all real numbers except where the denominator is 0. So let's think about it. The domain of f at x would be all real numbers. The domain of g at x is all real numbers. And the only time this calculation would be undefined would be whenever you're dividing by 0. So we're going to have to look at what happens when you're dividing by 0. Sometimes it's not possible for this function to be 0, but if it is 0, you end up with a discontinuity. How about the range? The range is best determined by examining the graph of the function. So if I was taking a look at this one, see, I would need to know where that point was and that point was to determine what the range was. Determining the domain is easy because I can do that algebraically. I can just look at the function and figure out where the denominator was 0. This one we would need to know exactly where that point was. And this one is very complicated. Look at all the little twists and turns there for us to try and figure out what the range would be. And in this one I would need to know where this was specifically. So end behavior analysis can help us find horizontal asymptotes, that these pieces there. If we want to know the range for certain, an algebraic technique would require the use of calculus. So I will be selecting the curves I have you graph very carefully, and I'm certainly not going to ask you to state a range, especially if it's going to involve using techniques from calculus. All right, a question I want you to think about now is how would the zeros for h at x compare to the zeros of f at x and g at x? And I'm going to pause just to give you some time to think about that. Alright, so if we want h at x to be 0, h at x is defined to be f at x over g at x, so f at x over g at x. And if we have a fraction of the form a over b, if we want that to be 0, then that's going to imply that a must be 0. So what will happen here is that h at x is going to have its zeros wherever f at x has its zeros. All right, moving on to the next slide. Rational versus polynomial. So polynomial functions are continuous, which means I could trace from the left end, from negative infinity, all the way to the right end, positive infinity of this function without lifting the pencil. So it's a smooth, continuous curve. Rational functions might have breaks. They don't always have breaks, not a guarantee. There's only going to be a break or a discontinuity if g at x, which was our denominator, if it's possible for that to be 0. Then what's going to happen is we're going to get a discontinuity. So notice what happens here. Trace, and the only way to get to here was to lift the pencil. I'm tracing that piece fine, but the only way to get to this piece is to lift my pencil. So we do have discontinuities here. The discontinuities I have right there happen to be vertical asymptotes. And again, I mentioned they're going to occur at the points where g at x is 0. in analytic geometry, we talk about what an asymptote is. I'm going to look right now. Let's look at the horizontal asymptote here, and let's look at the distance between the curve and that asymptote. And do you see how the distance between the curve and the asymptote is decreasing? So it starts to approach 0. So the distance between the curve and this horizontal asymptote is approaching 0 as we head to infinity. And now let's look at it this way, because here is a vertical asymptote. Notice how I had to, I guess I'm going to call it infinity in the y direction, the distance between the curve, so the curve on the right here, and the y-axis. Notice how that distance is decreasing. And it's tending towards 0. That's how you know you have an asymptote. If you have an asymptote, the distance between the curve and that line, also could be a curve, if that is approaching 0, then you definitely have an asymptote there. All right, some thinking for you. So here are some guiding questions. Thinking of, I'm just going to write this over here again. So we're looking at f at x over g at x. That's our rational function. The quotient of two polynomial functions. If I gave you a function like this, how would you decide where there would be vertical asymptotes? Can a rational function cross a vertical asymptote? How can you tell whether you'd have a horizontal asymptote? Can you cross a horizontal asymptote? Is it possible for an n behavior asymptote to be a diagonal line? So those are kind of some guiding questions. And then what I want you to do is, I'm going to suggest you head into Desmos, and you are going to graph each one of these. Let's take a look at the first one, just get some of it going now. The degree of the denominator looks like 2. The degree of the numerator is 1. How many zeros does the denominator have? Well, the denominator factors into x plus 4 times x minus 3. So it looks like it has 2 zeros. The leading coefficient of the numerator is positive 1. The leading coefficient of the denominator is positive 1. And now, I'm just going to pause for a sec because I want to open Desmos. Alright, so I went and I opened Desmos and I graphed x plus 1 over x squared plus x minus 12. And we can see we have a vertical asymptote here at x equals negative 4. We have a vertical asymptote at x equals plus 3. And we do have a horizontal asymptote at y equals 0. So coming back over to here, I didn't have enough room to squeeze this in, but I should have written x equals negative 4. I suppose maybe I can squeeze the y in here. There's a horizontal asymptote at y equals 0, and there is no oblique asymptote. So I'm going to suggest you shut this off. It's probably going to take you about 20 minutes or so for you to fill all of these in. So I modeled what you're doing. Remember the leading coefficient, find the term with the highest degree. For example, if we're looking at this one, the leading coefficient of the numerator is 6. Leading coefficient of the denominator is 2. The denominator, actually, I don't think that was the number of zeros. I think I wanted that to be the location of the zeros. So there's one at negative 4, and there's one at 3. So this will have a 0 at negative 1/2. The degree of the denominator is 1. The degree of the numerator is 1. 6x plus 2 over 2x plus 1. 6x plus 2 plus 2 over 2x plus 1. 2x plus 1. We'll hide that one. And then taking a look right here, we're ending up with a vertical asymptote right here, which looks like it's x is equal to negative 1/2. And we've got a horizontal asymptote right here, which looks like it's at 3. So coming back here, I'd be writing y equals 3, x equals negative 1/2. And there's not one of these. So I'm going to suggest you take about 20 minutes to half an hour to fill all of these in. And in the end, you should be able to take a look at one of these and tell me what you expect. Do you expect there to be a vertical asymptote? Do you expect there to be a horizontal? Or do you expect there to be an oblique? And then you can look at the answers, which I have posted. So I'm going to pause, and for you it should be a very long pause. So this is what the graphs of all of them should have looked like when you graph them. 2 vertical asymptotes here, 1 and a horizontal. Vertical asymptote, horizontal, y equals 0. 2 vertical asymptotes, horizontal asymptote. 2 vertical asymptotes, horizontal asymptotes at y equals 0. Here we have a horizontal asymptote at y equals 3 and a vertical. A horizontal asymptote there, that looks like it's about 1.5, and we have a vertical asymptote at 0. This one has a horizontal asymptote, looks like somewhere around 2. And then we have several, well, we have 2 vertical asymptotes. And then you can see what's happening in that picture. And then in this particular one here, we ended up having a hole in the graph, right? You were expecting to see perhaps an asymptote at -1/3, but you can factor a 2. So I'm going to write that over here. You can factor a 2 out of the numerator and you get 3x plus 1 divided by 3x plus 1. Those will divide. And you're left with 2, but we do know that in order to be the same function, x cannot be equal to -1/3. So you're going to get a hole in the graph there. That also happened on this one, because this factors into x minus 2 times x plus 2. And the denominator is 2 times x minus 2. So those divide, and we end up with x plus 2 over 2. But we're going to have to note that x cannot be equal to 2 in order for it to be the same function, because there is a discontinuity. Now, if you were to graph this in Desmos, you wouldn't see the discontinuity, but more on that later. So there's a hole in this graph. This graph has a vertical asymptote, and then it does have an oblique asymptote, or a diagonal asymptote. Let's see if I can grab a line here and change its color. Wow, that's way too thick. Let's just change the color on that one to green. And then I just want you to see that right through there, there's a diagonal asymptote. Now if we're taking a look at this one also looks like it has a diagonal asymptote right through there. This one has a hole. This one actually is not a rational function because we're dividing by 4, so it looks like just your standard parabola. This one has a vertical asymptote, and look on the ends, it's approaching some kind of parabola right through here. I'm going to need to just go back and grab the pen for that one. That thickness is probably fine. And so on the ends we're heading toward a parabola. And it looks like on the ends of this one we're heading toward a parabola. So it looks like the end behavior asymptote for those two are parabolas. I'm going to presume you went ahead and you took a peek at this because those were all the right answers. And then I had another page where it showed you sort of long divisions if you wanted to be certain what was happening on the ends. All right, so now we'll talk about a rational function. Bit of a summary now. You could have a hole. When might you get a hole? So if for a rational function f at x over g at x, if you can find a spot, so I'm going to call it A, where f at a over g at a is 0 over 0, then it might be a hole. Such as, I want to go back now to that slide where I showed you over here. So if we plug in a 2, notice how when x is 2, I'm going to write over here again, when x is 2, you get 4 minus 4 over 4 minus 4, which is 0 over 0. So if you get 0 over 0, you may be a hole. All right, let's move back over to here. A hole is going to occur, as I showed you in that previous example. You have a common factor where something might factor out. When it factors out, there's a potential for a hole there. Now here's the dangerous side. I was telling you, if you use graphing software, so look at this one here. Come back here. So I had tried to simplify. Was it that one I simplified for you? Or am I giving you a different one? So what's happening here is Well, let's check. I'm not even sure that I'm graphing that one over there. No, see, I turned this the other way around because this one here wouldn't have a, this one wouldn't be a problem. That's the one I was looking at right now because this is going to be x minus 2 times x plus 2 all over 2 times x minus 2. And then what would happen is that's going to look like a line. That's going to look like this one here. Very close to 1/2. Yeah, that's this line right here. And at the spot here that we factored out, which was 2, we have a hole there. So that's the graph of that function. So what's happening is we end up having a hole here. Now, if I flip this the other way around, and I've done x squared minus 4 over x minus 2, we still have 0 over 0. We have 0 over 0 here. We have 0 over 0 in this case. But in this particular case, we ended up with a vertical asymptote over here. All right, I'm going to move forward and actually just turn that. This is 2 over x plus 2. So this vertical asymptote is as a result of this. We still have a hole over here, but you can't see the hole. So I'm going to draw it in for you physically. So this picture came from Desmos, but I had to put this hole in so that you can see it. This is what you would have seen in Desmos. You can't tell that there's a hole right there at 2. So you have to be careful when you use graphing software. I am showing you here. I plugged in f at 2. F at 2 was coming back in as undefined. Okay, moving forward to summarize. So in this particular case, x plus 2 over x plus 2 all squared. Look what's happening at 2. So here we are at negative 2. I'm going to get 0 over 0. But here I have an extra factor in the denominator. And that extra factor in the denominator translated to a vertical asymptote here. Now let's take a look at the second one. This is also 0 over 0. But we have an extra factor in the numerator. So this one is going to simplify to just x plus 2. Whereas this one's simplified to 1 over x plus 2. So we still retain a vertical asymptote here. But in this particular one, what we do is we get a hole in the graph at negative 2. So be cautious. In order to get a hole, it is mandatory, right, to have 0 over 0. But it's not sufficient. We have to make sure that we weren't this form here. So rational functions of this form definitely will have a vertical asymptote at a if when we plug this in, f at a over g at a, we get a 0, but only in the denominator. So let's take a look at this example over here. So let's look at f at 2. So f at 2 is going to be 3 over 0 times 5. That gives me 3 over 0. Definitely have a vertical asymptote there. Let's look at the next one. F at negative 3 is equal to 3 over negative 3 minus 2 is negative 5 times 0, which is 3 over 0. So in both of these cases, because the numerator is non-zero, you definitely get a vertical asymptote there. All right, now I'm going to pause, and I'm going to give you, I want you to pause too, because I want you to read through that summary. Rational functions of the form f at x over g at x, where f and g are polynomial functions. Well, you will get a horizontal asymptote whenever the degree of g at x is larger than the degree of f at x, or the way I've written it here, the degree of f at x is less than the degree of g at x. So in this case, 2 over x plus 2. The degree of the numerator is 0, the degree of the denominator is 1. That's why we're getting that horizontal asymptote over there. You'll get a horizontal asymptote, but not at 0, at y equals a, when the degree of the numerator is equal to the degree of the denominator. So let's take a look at this next example we have over here. The degree of the numerator is 1, the degree of the denominator is 1, and now we have a horizontal asymptote happening at y equals 3. An alternate way to do this, to figure out what's happening, just in terms of the ends. What are you going to get for an end behavior asymptote? Because that's what these horizontal asymptotes are. They're happening on the ends. You can do a long division. So we've practiced this already. 2x plus 1 into 6x plus 2. 2x goes into 6x 3 times. So now I'm going to do 2x times 3 is 6x. 1 times 3 is 3, and then I'm going to subtract these. 6x minus 6x is 0. 2 minus 3 is negative 1. And that means that 6x plus 2 over 2x minus 1 could be rewritten as 3 minus 1 over 2x plus 1. And then I'm just going to extend the page just to show you that that is indeed the case. Getting a common denominator. 3 times 2x plus 1 minus 1 all over 2x plus 1. That gives me 6x plus 3 minus 1 over 2x plus 1. And there's our 6x plus 2 over 2x plus 1. Now, what is the advantage of writing it in this form? So we're going to think about sending x to infinity. Maybe I'm going to just write that off to the side. We're going to send x to infinity. What's going to happen here? So we're going to start heading toward 3 minus 1 over 2 times infinity plus 1 is going to be infinity. And that's going to be 3 minus. This is a number close to 0 but positive. So this is heading to 3 minus a positive number close to 0. So this is going to be very close to 3 but below 3. So notice on our graph over here as we went to positive infinity, see how it's approaching 3? Right here it's approaching 3, but from below. What's going to happen when we head to negative infinity? I'm going to try and write that up here. As x goes to negative infinity, then this would become, we're plugging into this one right over here. So I'm plugging into there. This is 3 minus 1 over negative infinity. Because when you plug negative infinity into there, 2 times negative infinity plus 1 is going to be negative infinity. And this is 3 minus a number close to 0 but negative. And that's the same thing as 3 plus a number close to 0, but writing it as a positive. And that means we're going to be approaching 3. Mathematically, we say from above, and that's exactly what's happening there. We are approaching 3, but from above. All right, when do you get an oblique asymptote or one of those diagonal asymptotes? So, if the degree of the numerator is 1 more than the degree of the denominator, for example, let's say we had an x cubed, a bunch of other stuff, and we're dividing by an x squared with a bunch of other stuff. After we do this division, we know that the degree of, notice here after we did this division, right? There is the degree. That happens to be our quotient. We know the degree of our quotient will be the difference between those two. Because after you do that division, that's what would be left. So you're going to have an oblique asymptote when the degree of this one is 1 more than that one, because when you subtract those 2 degrees, you'll get 1. Now, if we want to know exactly what the equation of this line is right here, I have to do a long division. So in this case, I'm dividing 2x plus 5 into x squared minus 4. Notice the difference in degrees here is 1, so we were guaranteed to get an oblique asymptote. I'm now going to have to multiply 2 by a half x to get x squared. So 2 times a half x is x squared. 5 times a half x is 2.5x. Subtracting gives me negative 2.5x. Bring down the minus 4. I'm now going to need to multiply 2x by negative 1.25 to get negative 2.5x. So that times that is negative 2.5x. And that times that is negative 6.25, and again we're subtracting, so there's 0 here, and that take away that is positive 2.25x. So we talked about our function, dividend divided by divisor is going to equal our quotient, so there's our quotient, plus our remainder out of the divisor. And notice, when we head to infinity, this piece is going to tend to 0. So send x to infinity. We're going to get this constant 2.25 over infinity, and this piece is going to tend to 0 positively. If x goes to negative infinity, then we're going to have 2.25 over negative infinity, and now that piece is going to tend to 0, but negatively. So I'm going to just erase this for a sec just so that you can see this a little more clearly. So when we went to positive infinity, we did that division and we said we'd be heading to 0 positively. So here's this equation of the line, and we're adding a positive number to it that's close to 0, which pushed us just above the line. See how we're just above the line right there? When we headed to negative infinity, I pointed out that we'd have 2.25 divided by negative infinity, which is going to be close to 0. I just want to make sure that's clear to you. That's negative. So we're heading to 0 negatively. So here's the equation of a line, and we're going to add 0, a number close to 0 to it, but negative, which is going to make us fall just a little bit under that line. And that's what's happening right there, just a little bit under the line. Last summary now. If we're dividing f at x by g at x, we're going to get a curvilinear asymptote when the degree of f at x is 2 or more larger than the degree of g at x. Again, if we want to find exactly what the equation of the asymptote is, then we can just do a long division. So this one is degree 4 divided by degree 1. That's going to give us degree 3 for the quotient. So we're going to approach a cubic on the ends. This is degree 4, that's degree 2. So we're going to approach a quadratic on the ends. And let me just kind of sort of attempt to, we were coming sort of through here, and that's really shaky. Coming like that. There's the cubic function that it's approaching. And in this particular case, I just want to give you a feel for, there's a quadratic. I'm not the most perfect of sketches through here because I'm trying to do this on a trackpad, but I just want you to see that the shape of the parabola that would be there. And again, that's happening because when we do this division, the quotient would have degree 2. When we do this division, the quotient would have degree 3. All right, so that's just a quick summary of the properties, and then we'll do more applications of this. I would suggest that you do some homework from the textbook to just further solidify your understanding of this. Again, thanks for watching. Hope you're finding these videos useful.